let's get started. I want to point you guys in the direction of a nice article written on using truncated proposals. So in your homework where you're coding up the Gibbs Sampler, the Metropolis Hastings sort of thing, if you want to embed those Metropolis steps and you're curious on how to do it, you will be getting this in future homework. I think I just said on the current homework, just implement the Gibbs Sampler. And that converges very, very quickly. But there's a nice write-up on using truncated proposals. This is by Darren Wilkinson, and so there's a very nice article on this. So it kind of tells you about different proposals that you might use. So when you come up with the acceptance probability in the Metropolis ratio, and so that's what this is right here. They talk about a correct implementation when you're doing all of this, and how everything should work. So in the example where we're trying to learn phi out of a normal model, that's going to be gamma distributed, you know, after I marginalize out all of the mu's, so, or just the mu. And so here's the theoretical answer that we can work out. That's the red line. And if you sampled using Metropolis, you'd come up with a histogram representation of that red line. And so, and they look the same, passes the eyeball test. Those are the same things. They talk about if you use a truncated proposal and you make the mistake and you say that it's symmetric. So it feels like it's symmetric for a second until you realize the level of truncation is different in the proposed move and trying to go backwards. And embarrassingly, for about the first couple weeks that I was playing around with this algorithm and I was turning in homeworks, I had that coded up wrong in all of my examples. My teacher could never catch it. And so Derek Wilkinson shows what happens if you assume symmetry. You don't write in the inverse ratio proposals. It's just the normalizing constant part that doesn't cancel out from the truncated normal. And this is the answer that you get. So in a typical problem. So you can barely detect that it happens. Basically that ratio, the inverse ratio of proposals, on average is pretty close to 1, is what ends up happening. And so I'm not suggesting that you code up the incorrect thing. I'm just showing you a direction of how you deal with this problem. So there's a couple different ways that you can do it. You can use the truncated proposal for updating phi, or you can transform phi to maybe log phi, so call that psi. That will make it live between negative infinity and infinity, and then you can use a non-truncated proposal. It just depends on if you want to do some math up front. What's your preference? What do? I just do it with phi. So I never really do the log transformation. I could probably make some of my code work just a little tiny bit faster. And so, but no big deal. Just because I wouldn't have to do those functional evaluations of the normalizing constant at every step. So some trade-off there. Something for you guys to read through. I want to come back around to mixture models and just finish the discussion about finite mixture models. And where we were last time is we were trying to understand what is the probability of each Cj being I. So what this says right here is that Xj came from component I. So that's what this whole thing says right here. That's the probability of it. How do we get it? We use Bayes' theorem. And so I kind of buttered up the notation in the mixture representation to condition on the Cj's. So for every Xj that we get, it came from one of the components. And the parameters are specific to that component. And so I can write that thing down. This looks a little redundant, that it's coming from component I, because that's what this says as well. But I like writing in that notation because now I know how to apply Bayes' theorem. That is the thing that we're trying to learn. So Bayesians, anything they don't know in their model, they throw a prior on. Hopefully it's a judicious prior, it's a good prior. And you just flip the thing around and put a probability distribution on it. If you don't know how to sample from those things, usually Bayesians run off to their Metropolis samplers. And they run those, and they sample everything, and then they just play around with the samples. They learn everything they need to know about that distribution. So that's kind of modern business for Bayesians. There can be faster ways to do everything, but this is a good starting point. So I would say 15 years ago, what I'm telling you is state of the art. So it's still a useful tool though. And so I'm just gonna flip everything around by multiplying by my prime, right here. And if I want to get rid of that proportionality sign, then I just normalize over all the other components. So same exact thing. So I'll just write down this part right here, the normalizing constant. It's just going to look like this. So I'm just going to look over my I goes from 1 to C, F, X, J, C, J is equal to I right there. And then I have the model parameters, mu I and phi I. Then I multiply by my prime. C, J is equal to I. So that's what it is. What I usually code up when I do this evaluation, I just write it up to proportionality. I usually don't compute every single one of them. I can compute all of the components, model probabilities, minus 1, because I know what they add up to. And so it turns out in most sampling built-in functions in R or MATLAB, when you say I just want to draw from a multinomial distribution, you can put in the weights up to proportionality and it'll normalize them. And so if you just want to save a little bit of time. But this is really just an application of Bayes' theorem. And so I can learn for every step of the Gibbs sampler, given all the other parameters, what I think these things are, right here. And so this is just fully model-based clustering, you might call it. So I call this clustering or mixture model inference, but it's the exact same thing. So clustering is the same thing as learning from mixture models. We'll talk a little bit more about that later. So the Gibbs sampler for this is just a couple iterated steps. So I'm just going to run this thing in a for loop. And I'm going to update my model parameters. So I'll just write for each component. So there's C of these, cap C, update. The model components. Given your C1 all the way down to C, did I write N? It's J's, capital J. And so I'm just going to update every one. So here's the idea. I need another step right in here. So there's one more step. I'll write it down in a second. I'm going to update given all of my C's. So if I know which component I think everything came from, how am I going to do this? I'm going to flip some coins. And so I'm going to draw using these probabilities right here. So basically I'm going to do this for every one of the C's. I've got its probability of coming from a particular component. So I have a cap C-sided coin, I give it a flip, and I do that for every data point. And I figure out probabilistically where I think the X's came from. And so I'm going to do that for all of these C's. So given the C's, then I can learn the model parameters. How do I do that? I'd probably learn mu first and then phi for each one, and then I would just iterate through each one of the components. And so, just like Sierra showed. The second step is, given the model parameters, I'm going to learn the C's again, and then I'm just going to iterate. So I need some initialization in here. So we've got to initialize. The better it's initialized, the faster it will run. Faster it will converge. This part right here is going to be update the C's. C1 to Cj. So I'm going to initialize my model parameters. I'm going to initialize all of my C's. How do you initialize the C's? Anybody have a strategy?
Uniform.
Maybe, yeah. So maybe I just draw it random and I want to make sure my code works good. And so I want to mix it up as much as possible. I want to do it a whole bunch of times. Make sure that my code's robust. What if I figure out my code's robust, it'll converge, but I really want to converge quickly? How might you initialize the C's?
Just choose the max.
Maybe the maxes, yeah. So maybe I plug it into this equation, but I don't know the mu and the phis for each one of them. So could be good, might not be good. If you knew what the mu's and the phis were, you could plug them in and compute it, but you don't know. Not yet, anyway. Anybody have any strategies?
Is there a reference prior for this?
Maybe there's some sort of a reference prior. So we're going back to this right here. What should I use here? That's up to you. And so typically people use uniform on that. So if you didn't know anything, what you will see in a lot of built-in software is they'll give you control over that. So imagine you were trying to classify spam, no spam, something like that, and you knew how much spam there was out there in your spam filters. You might calibrate your prior using it.
99.9%.
Yeah, exactly. A ton of it.
So you could also do something like a 1D k-means to initialize.
I love it. So how about k-means? Something like that. So initialize. Maybe using k-means. If you don't know what this algorithm is, that's okay. And so imagine I have some data. K right here is our cap C. So that's what you plug in. So maybe I know there's two components in here, and what it does, k-means, is it iteratively computes the mean of something. So it starts with an initialization. How does it initialize? Maybe uniform, but it can converge really quickly. So I start with some means out of my clusters. And so maybe my original initialization is all messed up, and I have two means that I've computed, and they're here, and they're here. It's my means. Mean 1, mean 2. Then what I do is I look at every data point and I see which one is closer to that mean.
So it chooses those points to minimize the total distance between the closest points to the mean?
Yeah, that's right. That's what it's actually doing. And so it just gets these things closest to its means. So what it does for every data point, compares them to the mean, sees which one is closest, and then assigns it to it. Then it computes the means after I have all my assignments. And it does it again and again and again. Kind of has this sort of Gibbs feel to it. Turns out, this algorithm is extremely related to mixture models. And we'll be going through that a little bit later. So if you guys just want to hear, k-means is this exact same algorithm if you believed all of the phis were the same in each component. And so at least is coming up with a solution to solving that mixture approximation. It can go really poorly, and there's other ways to encode k-means as well. But long story short, maybe use k-means as an initializer, please.
That's the distance matrix method one.
Say what?
That's the distance matrix method one.
Wildly. So totally. So
What's the question?
does the distance measure that you use? So k-means uses the L2 distance, and it compares it to a mean. And so what she's asking is, what if I changed it, instead of looking at my L2 distance, my squared air distance, and changed it to absolute value? So I think that's called k-metoids. And it can make huge differences. You can also calculate and use your scale distances, building in a phi. And if you do that in high dimension, that's called Mahalanobis distance. And all of these things can make a big difference. So I think we'll come back and we'll compare some of what we're learning in a Bayesian context to some of these machine learning algorithms a little bit later. But in a nutshell, yeah, it makes a big difference. We'll go through all the assumptions of these algorithms and when you would expect them to work. But usually I use these fast, clunky algorithms to initialize stuff, and then I throw it into my Gibbs sampler and I refine the answer. So that's how I like to put it all together. But you have choices. So that's really it. Iterate the model parameters, update them, and then update the C's. Back and forth, what you're going to get is you're going to be drawing jointly all of the mu's, the phi's, and all of the C's. You're coming up with a probability distribution over this very high dimensional thing. That's kind of cool. And so, again, one thing that I like about updating the C's is it can be done in parallel. And so I can compute all cap J of these as fast as you can compute one of them. Why? Because I just do it all simultaneously if I have enough cores. And so I tend to think we all have enough cores these days. It's pretty impressive. So later on, we're going to go through and we're going to try to get rid of this assumption. So that's where we're going to go in the future. But in an upcoming homework, I'm going to have you code this up. And so I'm going to have you code it up in this one-dimensional space. Everything we've talked about is 1D. And then I'm going to have you do it in higher dimensions as well. So we need a set of lectures before I can have you do that, because I have to teach you about Wishart distributions. So you'll know how to update the covariance matrix. Are there any questions about any of this? Makes a lot more sense once you have it all coded up and you do it. So if it's not clear now, it will be clear. So if you want to get a head start, go ahead. Okay, I want to show you a couple of numerical issues that you're destined to encounter. I know that a lot of you already know about these issues. You know what to do. You've been programming on a computer for a while, and you know if you just take everything we write down on the chalkboard and we plug it into our computer won't work. Our programs won't work. We just need a couple practical things. I want you to always be thinking about this sort of stuff. That when you run your code, you should be looking through it and making sure that you have numerically stable code that can work under all kinds of different conditions. So we're back to my original Gibbs sampling implementation. So we're moving away from mixture models and just going back to this one component thing. Keep in mind, when you're just sampling the one component thing, that's this piece of code. There's no CJs that need to be updated. You're just walking through this. So let's go to my code and just see how it runs. And so I want to show you a few things. So let me just generate some data. Same true sigma, true mu. So I think true sigma was 5. Is that right? 5. And true mu is 42. Okay. So let's generate some data. Boom. I've got 10 data points. And I'm going to run my Gibbs sampler code. So what my Gibbs sampler does is it does Metropolis steps for updating the mean and the variance. Why am I doing that? Because I'm pretending I don't know how to sample from something that I do know how to sample from. Just to demonstrate some issues. Your code will work a lot better than this code. So I'm going to hand it true mu and true sigma, but I've done something pretty cheeky here. And so I'll walk you through a couple things. I usually have, we'll talk about thinning a little bit later, but it's basically, you might say, I don't want every sample, I want every 10th sample. And the only reason you ever do this is just because your code is converging slowly. Everything's very, very correlated. And if I take a random sample from a sample, it's still a sample. So sampling from a sample is a sample. The only reason that we'd want to sample from our sample is because it might be much smaller. So we want to get rid of maybe every 10th. We only want to keep every 10th draw because I only want to store all of that. So it's just a storage issue. Talk a little bit about it later. I actually had it turned off. So I have a step size that I jump through. So this is my proposal variance. And I can tune that. I've just picked some number and I want to see how well it works. This is what you would tune in a Metropolis sampler. I have some number of iterations I want to run this for, and then I have some burn-in. So I'm only going to chop off the first value. So I probably need more burn-in, but I've got to run this code and see how long I need to burn in for. And then I have initializers. And my cheeky thing is I took the truth and I initialized it the truth. And so if my code works, then I'm already in stationarity. So I've started at the stationary location. So there would be no burn-in. And so theoretically, this code is supposed to work. Let's see how well it goes. I usually pad all of my storage first. You guys know why you would do this. Somebody help me out. Why do you usually build your storage in? You usually build
It
that.
has to resize the array otherwise every
Yeah.
step.
That's right.
So writing that to memory is expensive.
Exactly.
Sometimes resizing an array has to copy the whole array to a different location in memory.
Yeah, that even worse, right?
That's-
Yeah.
Yeah, so what they're saying is that as you keep getting a new element in your array, and it doesn't have storage for it, this isn't C or anything like that, it's gonna automatically deal with the memory management. So what it does is it makes a copy of that whole array with an extra spot opened up, and then it stores that thing and it wipes out the old array. So you're using twice as much storage in every step effectively. And it takes a ton of time to do that. And so this can save you hours just by doing that. Okay, my initialization is I'm already starting in stationarity. How would I know to do this? You wouldn't in practice. You wouldn't know where to start. I have some plotting mechanisms, and then I've got some updating steps. So my proposal from you is just the symmetric random walk. And so just a normal distribution. I center it where I was last time. I have my step, and I divided it by 10 because I wanted to tippy-toe around the space. So this is just some tuning to make it converge kind of slow so you can see it. And then I've got my proposal and my current location. So my evaluations of my target, the numerator and the denominator, I'm putting them on a log scale. So instead of working in a ratio, I'm working with the log difference right here. So I'm computing the log of my product of all these normals. So it's just a likelihood function. So where's the prior? Well, it's 1, and I've pretended to multiply by 1. Usually don't actually do it. So, and then I went and I took the log. So this would be atrocious code right here. I've taken this big product, and then somebody told me, well, if I take the logarithm, it's going to take big numbers and make them small, and it's going to take small numbers and make them big. So computers don't like numbers that are too big because it only has so much storage to understand all the digits that represent that number. So big numbers are problematic for computers, and small numbers are problematic for the exact same reason that I need all the decimal representations of it. And so logs are really cool functions. They take big stuff, they make it small, and they take small stuff and they make it big. It also should turn that product into a sum of logs, but we haven't written it that way. It turns out sums are a lot easier to operate with on a computer than products. So if I keep producting things that are big together, they get big real fast. And I take things that are small and I product them together, things that are less than 1, and they get small real quickly. But sums don't do that. They grow slowly. And each element is usually stable. Okay, so I've got this code. I'm building in, this is really inverse CDF sampling right here, but what I've done is I've computed my log ratio. I've taken a uniform and I've seen if it ducks that log ratio. So I'm just saying there's an acceptance probability out there, and I'm checking to see if a uniform is less than that probability. And so if it is, then I've sampled appropriately. So, if it's bigger than that thing, if it's not, then I go to the other side. So either I accept or I reject. That makes sense. That's the way I code that up. So it's different uniform every single time. That's what that's generating right there. And I just see if the log ratio, the log uniform is less than the log ratio. Apologies for not writing this out as log on here. I just have been doing this for years, and I always just write proposed and current.
Do we have C here?
Say what?
Do we have C here? Which group? Which
He's
one?
just doing the 1.
This is just
Just
one.
one.
Yeah. So this is just this step right here. I'm not implementing this stuff. Yeah, so it's just 1. And we'll see how well this works. So let's give this a go. Works great. Worked really well. And so, why did it work well? Well, I had it initialized pretty well. So when I looked at all of these little functions, you ended up looking in my code, I'd have a distance between x and mu, and And since it's initialized right, all those mu's are close to x's. Here's all my samples, and everything looks like it ran pretty well. That's pretty cool. So your code, once it goes stationary, should stay there. And if it doesn't, you have a code again. Something's wrong. Let's just change my starting location. See how well this works, maybe. So I'll change this, my initializers. Come up with some different initialization strategies. So maybe I'll make this 200. Just making up numbers. Maybe I'll make this real small. So that means I think the variance is really big. Maybe I'll make this really big and it means the variance is small. So I'm actually starting this thing very far away from the truth, and I don't have a lot of variability to explain that. So when I go to compute things like this number is going to be astronomically big. So let's make this like 10. When this number's big, this number right here is small. And that's going to mess everything up on the computer. So give this a whirl. See how it works. Again, same data point. So it should converge to the same answer. I run this thing for a little while. Found everything. It's hanging out there. You can see that. So it doesn't look very good on this scale because I've got all the burn-in period. But look how it kind of came down real quick and then it flew over here. So I can never really predict the path it's going to take through the space. But it's walking up those tails stochastically. Here are my samples, right here. So I can kind of see that phi burned in real quick and mu took a while. And so I should chop off this whole burn-in period. And then I'll have a good histogram representation. So throw away this part of everything. Our answer is probably pretty good. So let's just verify that. Let's look at my burn-in. I've got
3,000, which maybe 3 to the same 0.
Did I get that right?
Yep.
Let's just run it again, see how it works. Sweet, converging again. I could have changed the starting location. Probably recommend you do that a whole bunch of times, see that your code works. Sweet. Doing its plotting thing, I've got a lot of samples here. Give this a second to update. Plotting all that stuff takes a long time. So here's our answer. Code worked. That's really great. Okay, so I'm prepared to just go ahead and use this code. So let's just get rid of the burn-in again. We know what that does. Let me go back to initializing it the truth, because that's got to be my best answer. It is the best place to initialize everything. So right at the truth, it's the massiest. It's probably really close to the massiest part of that distribution. And just run it again. This is what we got last time. Everything worked just dandy. I like watching these things. Of course, I don't watch this when I'm actually doing this in practice. I don't print to screen very often, and I don't update the plots too often. So I look at them at the end because it's one of the slowest things you can do on a computer. Okay, so everything worked great. All right, let's just try this again. Let me grab some more data. Oops. It's taking a sweet time.
Excuse me, but how do you cut the burn-in coding was so? I mean,
Take the vector, and I chop a whole
so you
bunch.
have to run the thing once to know what's going to happen, and then to chop it off. You cannot predict.
If you knew the answer. So yeah, you have to run it and then you learn.
Yeah.
And so what did I do down here? So it's just burn in. I just grabbed the burn in period. Totally chopped everything off. So I like to store the burn in because I like to look at it, make sure that I burned in. working. So everything ran. Let's just generate some more data. X. I want to put a whole bunch of data in here. 1,000 data points. So I've got a lot of data to look at. And I'm starting it at the truth still. Let's just run this thing. It's hard to tell if it's working. I've got a lot of data, so my variability in my parameter estimate should be small. So it's hard to tell. But we'll just run this thing. Again, I've started at about the best location you could pick. See if I run it for a really long time, maybe it fixes itself. That's at least the hope. So, but as soon as it's messed up, it'll never recover. These plots need to update. Maybe I shouldn't be storing so many samples. Cut that down in a second. What do you think? Looks converged, doesn't it? You can't even get more converged than that. So it's at the truth, too. It gave me 42. So that's the right answer. But I started it there. And if I started it at 142, it would be stuck there. And so what's happening? Well, we have to study the ratio that we're looking at. But effectively, the way I've coded this whole thing up is I've taken this big product. Let's just look at my updating steps. I've taken this big product, and there's 1,000 data points in each one of those products. And I've started it very far away from the truth. Or sorry, I started right out the truth. So even these distances aren't far from each other. It's just that I'm producting things together. And so small numbers are getting smaller and smaller and smaller. I've got garbage. I hope my log trick works, and it doesn't. If I plug in garbage into a logarithm, it'll give me garbage back. And so we shouldn't have written it up this way. And so let's just rewrite this real quickly.
You should really write it as a sum from the beginning rather than log of it.
You got it. So I should have written those right there. And so this is the logarithm right here. So it's e to the minus something. So when I take the log of it, this is what I end up getting. And so it's just this big sum. And I could possibly simplify that and use x bar if I wanted to update all of that. Remember, I'm not learning phi in that step. And so the only thing that tells us is x bar. But I've written it pretty crudely. So all I'm going to do is I'm just going to waste a little bit of time by summing this in every step. But it will work. And so, again, if you know about sufficient statistics, probably use x bar to do all of this and scale phi. And so let me write down a couple different options. Even though this is a little bit boring, it's going to save you lots of hours in your life. So remember, we've got this. I goes from 1 to n. Phi e to the 1/2, e to the minus 1/2. Let's throw phi in right there. And then I've got my xi's minus mu. So I've got this function right here. Now all I'm doing in this first step is I'm just interchanging my values of mu in the numerator and the denominator. And so I want to take a logarithm of this whole thing. And that's what I did in the first version of it, but this was a really terrible thing to actually code up. And so what should I do? I should change this to sum. I goes from 1 to n logarithm of all of these things. E to the minus phi over 2, xi minus mu. We'll notice that phi is constant in both the numerator and the denominator, so I never even had to write this thing down right there. So I could get rid of that, I could get rid of that if I wanted to, because in this Gibbs sampling step, we're only updating mu. So the phis are the same, and so they cancel out in the ratio. So I should probably get rid of all of that. I shouldn't write it down like this either. I should take the logarithm all the way through. So this is sum. I goes from 1 to n. Log of e is just going to be minus b over 2 xi's minus mu squared. Turns out this can be written in terms of x bar if you wanted to, and that would be the faster way to do it. You just computed x bar up front. What I really just want to show you is that while they're the same on the chalkboard, they do very different things on your computer. So if you become a Bayesian, you'll become an MCMCer. It's almost guaranteed. And this needs to be monitored all the time. If you've got problems with your code, I would look here first. What you're proposing, print out those values, where you're currently at, evaluate these things. Just make sure that thing never turns into a nan or an inf or something like that. As soon as it does, you can't recover. So let's go back up here. Same thing mathematically, very different on a computer. We'll run this again. 1,000 data points, now it works.
Excuse me, you mentioned that the 5 to the power half is acting as an normalizing constant, that's why we can remove it?
Yeah, so in this,
But aren't we iterating over it, so,
when I take the log difference, if you want to write it out, what we would have, if I did keep it, right here I have a log of this thing, so 1/2 log of that thing, that would be constant in both my log differences,
oh.
and they would cancel each other. So all the things that cancel each other, don't compute them. And so let this finish its thing. This is still updating. And there we go. There's our samples. You'll notice also, since I have a lot of data points, these contours became circles between mu and phi. That tells us that they're starting to look and feel more and more independent of each other. But there is some association there, and you see it with low sample sizes. Are there any questions about any of this? So again, this is really it. Just make sure your code is numerically stable, compute things on log scales. Logs make small numbers big numbers small in just the right fashion, and don't work with products. Work with sums. So how do you turn products into sums? Logarithms have a way of doing that for you. Then you have sums of something that's numerically stable. That's very nice. So that's what you'll be fussing around with if you become a Bayesian for lots of time in your life. If you ever see e to something, get rid of it. So that's going to mess up your code as well. So anytime I see that sort of stuff, I panic. And so then I've got all these little numerical things that I do. I've got all these identities that work on computers, and they usually concern logarithms. Okay?
So why does the independent look like a circle instead of a square?
So just think about like it can actually look like any sort of ellipse right here. So a square could do it. So, but if I have some distribution that looks like this, okay, that's actually independent this direction from that, meaning that the marginal distribution that I have right here is the same all the way through. Same thing happens down here. So squares will do it as long as they're axis parallel, but anything axis parallel. It doesn't change distribution as I march through one of the axes. Squares look like that. Rectangles could do it. Make sense? Okay. I think that's about it. So I think we can finish this lecture. Be done with the Gibbs sampling, so code all that stuff up. I'll be making these problems a little bit more challenging in each homework. And so, but get your programming, standards down. Work on these log scales. If it doesn't haunt you on this homework, it'll start haunting you later. I do have lots of numerical issues that I've built into problems. And so if you start finding yourself having difficulty with your code and it's crashing and you've got a whole bunch of small numbers that just keep getting smaller when you build in likelihoods. It's intentional. And so there's one really cool problem that's coming up that you may struggle a little bit with. To get a head start on this, I will say, imagine you had to compute something like this. So imagine, this is just something to think about. You had to compute, let's say I have some distribution, I'll call it pi 1, some disk. What you might want to do is take the logarithm of this thing to make it something that you can compute. But imagine you're trying to compute something like this. This is some other disk. What you'd like to do is compute logarithm of pi 1 plus pi 2 or something like that. So if I have two functions, maybe this isn't numerically stable, but the logarithm of it is, and I need to add it to something else. So I want you to just think about this. How would you actually compute this thing without ever computing a pi? And how would you do it if you could only compute log pi? So how would you represent this? So your challenge is to write this using only log pi 1 and log pi 2. That's a future homework problem, and this could give you hours of grief if you don't answer this question up front. So more later.